the exactness was not proved completely. So the remark on the exactness of the sequence. So I will comment just on one fragment of that, namely the principal part, which was written like this. So we had positive numbers on the edges of an ideal on the faces, and we continued with the first homology of the surface with multiplicative positive coefficients. But we had something in the left and something on the right, which is the essential part. So let me precise here that tau is with dot is a pointed ideal triangulation. Ideal triangulation of sigma. Okay, so what we do? So we take a tau check. Is it? Yeah, tau check is a maximally truncated tau. Truncated tau. So what does it mean? It means that this is a complement. It is the complement of largest open pairwise disjoint open disks centered at punctures. So an example. So if we start from a 4-puncture sphere, so then we can draw ideal triangulation like this. So we put one puncture at infinity, and then 3 punctures in the finite part, and then we draw the ideal arcs. So this is ideal triangulation of the sphere, where sphere is identified with a real plane with point at infinity. And then we start drawing disks around punctures, but in a maximal way. So we make them as big as possible, so that they become a pairwise tangent like this. And of course, also the disk at infinity, which looks like this. So what remains of the surface is this only shaded triangles. And we cut out those disks. So we end up, let me put it this way. So that's the thing we start from. And we go here to tau check, which is the shaded part of. And now we see that we naturally obtain a new cellular complex. So tau check is naturally a CW complex, where with vertex set given by midpoints of edges of tau, given by midpoints of edges of tau. Okay, so that's the first thing. And the two cells being triangles in the middle part of triangles of tau. Okay, so what we have, if we had a triangle T in tau 2, then we get a triangle T check living in tau check 2. Okay, and that here we have 3 vertices in the middles of edges. So we get a cellular complex like this, and then there's an easy remark. Clearly, tau check is a deformation retract of tau, right? Because our surface is punctured, so we have disks centered at the punctures, and then we just retract all radii of each disk to the boundary. So is it clear, this part? And now what we remark is the following. Now r power 2 tau dot 2 positive is identified with the group of cocycles in dimension 1 with the set of cocycles z 1 of tau check. So let us recall what was the definition of so let me finish this phrase. Set of cocycles, and r power tau 1 positive with a set of cochains C0 of tau check r tau dot with the differential is identified. Is identified with the differential in the cochain complex, right? And S tau dot with the projection identified with a projection to the quotient space. G1 tau check. With a boundary, right? So let me be more precise here. So what we had as a map S tau. So that's now our picture is like this. And if we pick up a distinguished corner like this, then if you look at the nodes of the last week, then here we put x1 over, so let me put here label x, which is a couple of positive numbers associated to this triangle, x2 over x1, x1 over x2. Then that was x1, and that was x2. But now, this time, I am drawing explicitly the edges of the new cellular complex. But last time, we've drawn intersections of those triangles with paths, right? And now we just realize any path of the last time as a edge path of the complex tau check. And now it becomes our sequence of two arrows becomes just a fragment of the cochain complex of the tau check. Okay, now I hope it is better with the exactness of that guy. Okay, now coming back to the end of last lecture. So let us recall that we have obtained a basic algebraic system from the Teichmüller theory. We have a basic algebraic system in the category of sets with Cartesian product as a monoidal product. We have a basic algebraic system given by basic VRW in a set given by. So V was identified with the square of the real positive half line, and the R is a map from V to V, which sends x couple of positive numbers to another couple of positive numbers, which will be denoted x check. And please pay attention. Last time I committed an error, so I mixed up R with its inverse. So now the correct formula is this: 1 over x2, x1 over x2. So if you compare it, I wrote another formula, but here I just remarked that x hat will be denoted, this is a notation, denoted double check, x2 over x1, 1 over x1. Okay, so that's two objects in the triple, and the W is a map from V squared to itself, and a couple of pairs of positive numbers x, y is sent to x dot y, comma x star y, where x dot y is by definition is x1 y1 comma x1 y2 plus x2. And the x star y is a couple of fractions with one and the same denominator. The denominator is given by the second component in the x dot y. And the numerator is given for the first component product of 1x and 1y, but the indices here are switched. So it is x2, y1. And here just y2 in the denominator. So that's the way I keep it, learned it by heart. Yeah, and last time on trying to prove this statement, so we derived a formula that this thing is equal something given in terms of hats checks and the dot operation. And the formula is this. So we have to switch hats to checks and vice versa. So it should be y hat dot y check dot x hat. X y hat, x check, and one big check. Let me check that. It's correct. Yeah, it's a good exercise on elementary arithmetics to verify this equality. Okay, if you lack some experience of elementary arithmetics, that's a good opportunity to fill this gap. Okay, so I think that with the correction, by switching all hats to checks, so the proof I've given last time is correct. But anyway, I put the notes of the last lecture where I corrected the checks and hats, so you can verify that. And now I'd like to point out one crucial property of this basic algebraic system, the crucial property of this basic algebraic system. Okay, so let me. The property of this basic algebraic system, crucial for quantization, is its compatibility with the symplectic structure. Symplectic structure on V given by two form dx2 wedge dx1 over x2 x1. You remember we wrote already this symplectic form to see some relation with a pullback of the Weil-Petersson. But here, no, we can now forget about Teichmüller theory or Weil-Petersson form, and just to think in terms of the basic algebraic system. And now we are going to check that it is indeed consistent with this form. So this will be a theorem. So the maps R and the W are symplectomorphisms. Symplectomorphisms. Where W is interpreted as a symplectic symplectomorphism with respect to the symplectic structure in V squared given by sum of two symplectic structures corresponding to two components. So formally we write it like this. So we have two projections. Projection 1, projection 2 to two components in the Cartesian square. So on V, we have written the symplectic form omega V, and we interpret the product of two symplectic spaces as a symplectic space by pulling back the symplectic structures on the components to the product. Okay, so the proof is not difficult, so let me present it from the SwissMAP R. So the case of R. So in logarithmic coordinates, x I equal e to capital Xi. We have omega V given by d capital X2 wedge capital X1. And R star X1. So is what? So we look at the definition of R. So first components in terms of initial coordinates is inverse of X2. So in logarithmic terms, this will be minus X2. Right? And R star applied to X2. So we should take this fraction and look at its logarithm. It will be X1 minus X2. Now it's an easy check that R star applied to omega V. So what is it? It is a d R star X2 d r star x1. So I reduce number of parentheses a little bit. And we use all this. So we write d x1 minus x2, wedge d minus x2. So we can forget about x2 here and switch the order by absorbing this minus. So this will be omega v. So R is a simplector morphism. So the second case of W. Again, in terms of logarithmic coordinates, let me introduce an auxiliary function. Denote f to be log of 1 plus x1 y2 over x2. So which is a function of capital X1 plus y2 minus capital X2. So it's a function of one single combination of coordinates. Then what we have? Then W star of x1. So we have to, what we have to do? We have to pick up the first component in this map, x dot y, and take a first component of that in logarithmic terms, which means that we have to pick up this guy and take its logarithm. So this becomes a capital X1 plus capital X2. Please stop me if I go wrong. I hope I am okay so far. Then, what is W star of x2? So we have to take a logarithm of that guy. But if you look at the capital F, then it is given by logarithm of that guy divided by x2. So which means that this is equal to F plus x2. And now I take W star of y1. So now we switch to that guy, x star y, its first component. Its first component is written here. So now I pull out x2 from here and cancel it with that x2. And the result will be capital Y1 minus F. And finally, W star of Y2. So we have to treat now the last component here. So we again pull out x2. So the result will be capital Y2 minus capital X2 minus F. Okay, that's the map. And now we start calculating. So W star of omega v squared minus omega v squared. So we want to arrive to 0 for that difference. So let us see. So dx1, dx2 with w star. So dx1 plus y1. No, we have to start from x2, sorry. dx2 plus f, which dx1 plus y1. So that's the first term here. Plus y2, it's d of y2 minus x2 minus f, which d of y1 minus f minus omega v squared. So I don't write it explicitly for the moment. And now I want to single out the terms which would cancel with that guy. So which means that I have to single out dx2 times dx1. So I write dx2 which dx1 plus y1 plus df which dx1 plus y1. So I am preparing to cancel dx2 times dx1. And likewise dy2 and dy1. So I write it like this. dy2 minus x2 minus f, which dy1 minus dy2 minus x2 minus f, which d minus f minus omega v squared. And now we can just cancel the terms which correspond to omega v squared. And it is a term dy2 dy1 and dx2 dx1. Okay, and then we work with the rest. So what is the rest? Yeah, so we can cancel a little bit more, right? Namely, the term dx2 y1, y1, it shows up twice with opposite signs here also. Right, dx2 which dy1, and here we have minus dx2 dy1. And the remaining part I am going to put, we can cross out f, because it goes like df, df. Is that all? Right. Thank you. So what color I can use yet? Blue. dfy1 with minus, dfy1 with plus. And I think that's it. Now we put the rest all together. And luckily, we have every way df, right? So we collect the term df and write the rest. df which parenthesis, and what will be in the parenthesis. So first we write this x1. And then So we can ignore these two minuses, but we have to switch to the other side df. So that makes the change of these two signs. So it will be df x2 minus y2. Or maybe no.
No, it's a plus because you had the minus sign already before. Just if you compare with the expressions in line above, then you see that you have to add one, to change one line.
So this is wrong, right?
Yes.
This was wrong. Yeah, thank you. Now it's okay. So we write plus y2 minus x2, right? And now we come back to this remark. So f is a function of x1 plus y2 minus x2. And you see that we wedging df with the differential of that combination. So this is 0 by the antisymmetry. That's the proof. So it's not very difficult. Okay, now that was the classical part. So the rest will be quantum. And we will start slowly the quantum theory. And let me put the title, Quantum Technology. So the idea is to quantize the basic algebraic system we have constructed by taking into account this symplectic property. But before going to quantum theory of this basic algebraic system, I'd like to spend a little bit time on general quantization ideology. Okay, so let me say the canonical quantization, but canonical in the sense of physics. So in physics there is a notion of canonical quantization, but it is not something well defined mathematically. It is very much dependent on the model you are working with, because the general quantization scheme is a huge still open problem, which is kind of solved in the case of deformation quantization. But we want more than just deformation quantization. And so to have more than deformation quantization, I can rely on something, on some general theory about that. So we will be here partly heuristic, but we will keep the mathematical rigor as much as possible. Okay, so what will be canonical quantization for us? So the canonical quantization deals with symplectic spaces. Spaces and symplectomorphisms. Okay, so to be, assume that we have a symplectic space. Let M omega be a symplectic space. And G, a group, a subgroup of symplectomorphisms. So we cannot hope to deal with the whole symplectic group. So usually I think that there are some no-go theorems saying that it's impossible to quantize the whole symplectic group. So in practice, we always deal with just some sufficiently small subgroup of the whole symplectic group. Okay, and then that's a Poisson bracket. Associated to m omega. Do you know what is a Poisson bracket? General definition. So it's some binary operation on the set of functions on the symplectic space. Associated to m omega is defined by the formula. But if you don't know the definition, we will see that it's not a big problem because we will manipulate the concrete things. So that's the thing. So we have two functions, fg, and we put them into a curly brackets. So this is so to distinguish from the set of two elements fg, I put pb as an index, so to indicate that this is a Poisson bracket. And it is given by x sub f acting on g. So here, fg are smooth functions on M, and xf is a vector field filter on M defined by the formula. If we contract xf with a symplectic form, then this will be the differential of f. Okay, after the break, we will see how this works in a simple example. Okay, so that's a Poisson bracket, and we continue after the break. Okay, so we have defined the Poisson bracket. Let us see example. So we take M to be real plane, and the symplectic form, the canonical one, so for some reason I write first x2 and then x1, not vice versa. So let us pick up a function C infinity of M, and we'd like to find xf. So this should be a vector field. So it should be some coefficient a times d over x1 plus b d over the x2. So we have to identify those coefficients in terms of function f. So we follow the definition. So the internal contraction of, I hope that you know this language of differential geometric operations. Okay, very good. Internal contraction of omega. So what is it? It is a anti-differentiation. So we contract first the leftmost term in the wedge product. So EXF applied to DX2. Okay, and this is a scalar. So we multiply it by what remains from the form. And then we put minus DX2 and contract xf with dx1. Okay, it's this minus because of anti-commutative nature of the internal contraction. Okay, so you know this. And now, so this is just a pairing between forms and vector fields. Dx2 xf paired with x1. And the pairing means that we should pick up the corresponding coefficient in the partial derivative. So for example, this thing is equal to the coefficient of d over dx2. So this is b, and this is a. Okay, so we have a b dx1 minus a dx2. But on the other hand, according to definition, so this should be differential of f, which is df over dx1 plus df over dx2 dx2. So this equality means that b equal df over dx1 and a equal minus df over dx2. So we find in a unique way the coefficients, unknown coefficients of xf. That's how the definition works. And now we can calculate the Poisson bracket. Now the Poisson bracket of f and fg is a function which is by definition application of the vector field xf to g. And so what is it? So we write xf, so a probably is better to start from second term, df over dx1, that's the coefficient b, d over dx2 applied to g, to dg over dx2, minus coefficient a, df over dx2, d over dx1 applied to g. So that's the Poisson bracket in our example, and in particular, if we try to calculate the Poisson bracket between coordinate functions x1, x2, then what is it? It's a dx1 over x1 times dx2 over x2. So it is 1. Okay, now let me describe this general ideology. So the quantization procedure will consist of 2 steps. So the quantization of m omega g, right? We have specified a symplectic space and a group of symplectomorphisms. Consists of 2 main steps. So step 1. So we choose one parameter family family of associative algebras, associative algebras. So actually, there are several advanced courses on dealing with quantum theory, right? In this semester. So it's a good thing to compare what I'm telling you here and what you are doing over there. They should overlap non-trivially. Okay, so a one-parameter family of associative algebras, let me put them this way, A sub h bar, where h bar lives in non-negative real numbers, and a group of homomorphisms, not group, group homomorphisms. So what I'm using some specific notation, which is not very essential. So parenthesis with index h bar, which goes from G to automorphism group of the algebra A sub h bar. Such that now we impose a certain set of conditions. So the first condition tells us that for any h bar positive, there exists an isomorphism of vector spaces over C. So at this moment we switch to the coefficient field to complex numbers, and there exists an isomorphism of vector spaces, which will be denoted by hat, which goes from A0 to A sub h bar. So in principle, this hat should carry also the index h bar, but I suppress it. It is assumed implicitly. Where A0 is identified as a subalgebra of smooth functions on M with coefficients in complex numbers. Okay, so we distinguish between A0 and all other H bar, all A's. And for A0, we just say that it should be given by a subalgebra of the algebra of smooth functions, complex value smooth functions on our symplectic manifold. And we demand that for any non-zero H bar, as vector spaces, they should coincide with A0. So the only difference in the multiplication. Second thing, if we pick up two functions, x and y, and take the images and take the difference, so of course this is a commutative algebra, but if we put a hat, we are in some algebra with h bar. So if we divide it by h bar, multiplied by the imaginary one, that's why we need the complex numbers. And then we take a limit when h bar goes to 0. Then we go to the algebra A0. So we should end up with an element of A0. And this should be nothing else but the Poisson bracket of xy. Xy, and in particular, it means that A0 should be closed on the Poisson bracket. So A0 cannot be arbitrary subalgebra. So at least to make sense of property 2, it should be closed under the Poisson bracket. And the third condition is that if we take a G inverse of G, parentheses with index H bar, so remember that we are taking the image of an element of symplectomorphism in the automorphism group, and take a limit when H bar goes to 0, then this should coincide with the induced map on functions of the symplectomorphism restricted to A0. So if we have a symplectomorphism, then we have a induced map which reverses the arrows on the level of functions. Actually, we used this already in proving the theorem. And so I don't like this inverse myself, but this star reverses the arrows. So that's why we need to reverse the arrows here. Okay, so that's a condition for this family of algebras. And if you know something about deformation quantization, then if you suppress the part dealing with symplectomorphisms, this is essentially the idea of deformation quantization. And now step 2. So it consists in realization of A sub H bar. Okay, so for any H bar positive, for any positive H bar, one realizes A sub H bar in a Hilbert space in such a way that, so what are the conditions? So the first condition for any real f in A0, real valued function on A0, the operator f hat. So f hat is an element of A sub H bar, but now it is realized as an operator in a Hilbert space. In a Hilbert space H. The operator is symmetric. So I put here the weakest conditions possible. Usually in physics they say that it should be self-adjoint. But in the case of non-bounded operators, one has to be careful because self-adjoint and symmetric is not the same thing. And any self-adjoint operator is symmetric, but not vice versa. Okay, and then the second thing concerns the symplectomorphisms. For any G in G, there exists a unitary operator G hat. So here I'm overcharging this hat notation, but I hope it will not induce any confusion, because I put hats on objects of different nature, right? So if we put hat over a function, then it is a quantized version of the function according to line 1, the part 1 in that blackboard. If I put hat over symplectomorphisms, then it will be a unitary operator, which I'm going to define. And hat in the R operation is something else. Okay. So the unitary operator such that. So if we conjugate by this operator an element x, with hat, it will be the same thing as acting on x hat for any x in A0. So saying differently, this condition tells us that any automorphism of our algebra, which comes from the subgroup of symplectomorphisms, is inner automorphism of the quantized algebra when they are realized as operators in the Hilbert space. Okay, now that's the general framework. And our goal will be to follow this line, these steps to cook up the quantization of our basic algebraic system. So we know already that they are given by symplectomorphisms. So all the initial data we have at our disposal. But before going to the basic algebraic system, let me describe by an example of that general construction in a simpler context of linear symplectomorphisms. Example, so we take M to be, again, the real line with canonical symplectic form. And G, we take as, again, our symplectic space acting on M by translations. So that's we pick up an initial triple of our objects. And it's easy to see. So let me write it G, Y1, Y2. So that's the element of G. And G, Y1, Y2 acts on X1, X2, and gives a X1 plus Y1, X2 plus Y2. And it's easy to see that the symplectic form is preserved because the differentials do not see the constant shifts. Okay, now what we do, let us do step by step. Step 1. So step 1, we have to pick up a family of algebras. And there is no recipe in getting the ingredients of the quantization, so it is a kind of art. So here I give just the answer, right? So I just define A sub H bar explicitly by a presentation. So it is generated by X1 hat, X2 hat with relation X1 hat minus times X2 hat minus x2 hat x1 hat equal I h bar. So, so that's the definition. And so the consequence, the A0, which should be a subalgebra of smooth functions, so is identified with the polynomial subalgebra of coordinate functions with complex coefficients. Then what we can try to check if the conditions of step 1 are okay. But we have to pick up this also. So G y1 comma y2 sub h bar acting on xi should be equal xi hat should be equal xi hat minus yi. I think minus sign is dictated by the. Yeah, here is a commutative case, so it doesn't matter plus or minus, but in general we have to invert things to have a homomorphism. And now what we check is this x1 x2 hat minus x2 hat x1 hat divided by I times h bar. This is a h bar independent, but anyway, by definition this is 1, which is the Poisson bracket of x1 x2, which we calculated in the previous example. Yeah, so formally, at least on the level of generators, so we are able to check that the properties we imposed in step 1 are satisfied, and this formula just does not depend on h bar. So if we take a limit of h bar, then this is indeed the pullback map. So this is also satisfied. Okay, so are there complaints about step 1? Then we switch to step 2. Again, there is no recipe for, which works universally in all cases. And in our example, we just give the answer. So step 2. So we have to pick up a Hilbert space. So the Hilbert space will be L2 of R. And we realize x1 hat as a multiplication operator. So I am using the Dirac bracket notation, with which you are familiar with already. And x get applied with x2 is minus I h bar d over dx. Okay, so we realize our algebra this way. Yeah, just here a remark that the commutation relation, defining relation of the algebra is preserved under this, because when we commute xi hats with shifted by numbers, then the commutation relation is not affected. So this is the automorphism of the algebra. Okay, now going back to step 2. So we will look for G hat y1, y2 in the form E alpha x1 hat plus beta x2 hat. Let us try to adjust the coefficients alpha beta in C. And using the Baker-Campbell-Hausdorff formula of that form, using e to A, e to B, e to minus A equal. Actually, for this part, we don't need even the realization. But anyway, let us use it do it algebraically. B plus A commutator B plus 1/2 AB 2 factorial plus and so on. And in our case, we try to conjugate by G hat y1, y2, xi hat, G hat y1, y2 inverse. So we have written G hats in terms of exponentials. So A is just this combination. B is a xi. So we have a xi hat plus alpha x1 hat plus a beta x2 hat, xi hat. And this is a complex number, this commutator. So no higher order terms in this infinite series. So we just have this formula. And then we can just calculate this commutator depending. Okay, they will be imaginary I, so let me put here J. So if J equal 1, then this term doesn't contribute. So we have beta x2 commutator x1, which is a minus I h bar. So we have a minus I h bar beta if J equal 1. So if J equal 2, this term doesn't contribute. So alpha times x1, x2. So it will be I h bar alpha if J equal to 2. And now we have to, we need to get this combination in the end. So that's minus I h bar beta should be equal to the coefficient in the case of I equal 1 minus y1. And A h bar alpha should be equal minus y2. So equivalently, beta becomes minus I over h bar y1. And alpha becomes I over h bar y2. So G hat y1, y2 becomes E I over h bar y2 x1 hat minus y1 x2 hat. So we found a particular solution for the intertwining relation. So and these are indeed unitary operators because now x1 and x2 are self-conjugate, if self-adjoint. So this combination with real y1, y2 is still self-adjoint, and we get an imaginary one as a coefficient. So this is a unitary operator. because as we learned in the introductory part on quantum theory, imaginary exponential of a self-adjoint operator always exists and is unitary. But we, as maybe you have noticed, we never demanded that these operators realize a homomorphic image of the group by unitaries. Simply because in quantum theory, in general, this is not true. And the reason is very simple, because we can redefine our operators by some numerical factors which do not affect the conjugation. Because numbers commute with everything, they are in the center of the algebra, so these operators are not defined uniquely. So there is an ambiguity, and even more, so in general, this unitary realization gives a central realization of the centrally extended group G. And often this central extension is non-trivial, which means that we cannot remove the projective factors by redefining the normalization of those operators. And this is an example of such a situation. So we can try to multiply two such unitary operators. And actually, we did already this few weeks ago, but we can just redo it in this context to see that we cannot have the homomorphism of groups. And the remark to make here is that these operators are generally non-commuting. So let us try to multiply two operators, G hat Y1, Y2 times G hat Z1, Z2. So is it G hat Y1 plus Z1, Z1 Y1, no, Z1, Y2 plus Z1. So in principle, we would like to have this. But in this example, it is not possible, because if we try to calculate this, then we use again Baker-Campbell-Hausdorff formula, which is really the BCH itself. If we multiply two exponentials with non-commuting A and B, then what we have? We have A plus B plus 1/2 commutator AB and plus higher commutator. But higher commutators are more complicated in this case than in that case. But anyway, the higher commutators will not contribute, because in our context, the commutator of linear combinations of x1 hat, x2 hat is a C number. This is a quantum mechanical terminology, C number, by the way. Okay, let us do this. So this product becomes, so we add things, E, so I, H bar, Y2 plus Z2 X1 hat minus Y1 plus Z1 X2 hat. So this is the part given by A plus B. And then plus 1/2 the commutator. And then we have to put a commutator Y2 X1 minus Y1 X2 hat, comma, Z2 X1 hat minus Z1 X2 hat commutator. And now what is this commutator? So X1 hat commutes with itself, but doesn't commute with X2. So we have y2 minus z1 times commutator of x1 hat, x2 hat, which is I h bar. This has been treated. Now, this term doesn't commute only with this term. So it is plus minus 1 y1 times z2, commutator of x2, x1, which is minus I h bar. Here I forgot something to put, right? I forgot the square over h bar, I over h bar. Because this is a common coefficient for everybody. And yeah, so if we simplify, so this part is already recognizable. So it is a y1 z1 comma y2 plus z2. And we have a correcting term, which is given by e2. So if we pull out minus I h bar and combine with this, then one I disappears, one h bar disappears. So what remains is I over h bar. And now we write just the coefficient of minus I h bar in here with 1/2. So 1/2 we can put here. And now minus I h bar, so y2 z1 minus y1 z2. I thought that I had a different sign. Yeah, it's okay. So that's a formula. So we see that, that this equality is not true. And, but this exponential is a C number, so in the sense that it is not an operator. It is just a complex number of absolute value 1, because all variables are real. And even more, it is antisymmetric in y and z. Since it is antisymmetric in y and z, but if we try to renormalize, if we try to redefine g hat 1 y2 by g hat y1 to y2 c of y1 y2 by looking for some functions of y1 y2 trying to absorb this projective factor. Then we will not succeed because the combination which will show up of C's will be symmetric in y and z. If we try, then we will have g hat y1 y2 g hat z1 z2 equal g hat y1 plus z1 y2 plus z2 as before. This exponential factor, which we just have calculated. And then the combinations of C's. So what is the combination of C's? It is a C of y1, y2, C of z1, z2, divided by C of y1 plus z1, y2 plus z2. And as you see, there is no way to choose function C in order to equate all this to 1. And this is the manifestation of the fact that as a cocycle over the group R2, this is non-trivial. Because this, if we would be able to absorb it into such combination, then it would mean that the cocycle is trivial. Because this is by definition the co-boundary of the function C. So it is impossible that this equal to 1. Okay, so I think we stop here today, and the next time we will be applying these quantization steps to our basic algebraic system. Are there questions? Everything is clear. Good.